Okay, so now that we've seen what continuities and discontinuities kind of look like, now we're going to give them names. And I'm really just going to do this by just moving along as I go. Okay, and I'm going to argue this from like calculus perspective. So what I mean by that is you're going to hear me use calculus terminology here. So it says that which x values do we have a jump discontinuity? And a jump discontinuity occurs from the last example wherever A is true, wherever both of your side limits exist, but B fails. So that's what a jump discontinuity is. The side limits exist, but they're not the same value. So where do we have side limits that exist, but they don't agree? At 1, that's where you would be able to say, okay, the limit from the left is 2, the limit from the right is 3, but you don't have a general limit. So there's 1, and also at 2. So one thing students start doing is they start thinking jumps depend on whether there's a closed and open circle. No, what matters is are those like endpoints connected or not. So because you do have endpoints, but they're not connecting, because you have an endpoint here and an endpoint here, and they're not connected, again, connected continuity, and because they're essentially jumping from, again, if you were reading a table, you'd be saying, okay, it's 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 1.99, 1.999, and then suddenly it's 3. So it jumps from 2 to 3. Same thing here, it jumps from 6 to negative 7. Now this one right here would just be called a removable discontinuity. In other words, it's like this one circle just needs to be filled, but they've removed the filling. Okay, so jumps, and we've now seen removables as well. There's only one more type you're going to see, infinite discontinuity. And that is when your left or right hand limit suddenly is going to infinity. So that's what's happening here at negative 5. Negative 5 is your infinite discontinuity. Sorry, x approaches 5, not negative 5. It's the left is going to negative infinity, the right's going to positive infinity. Those are an infinite, because we're going to a certain side of infinity, discontinuity. That's the only one, because again, this is the only other discontinuity, and that is a jump. Now, why do they include negative 1? I don't know why. Negative 1, nothing's really going on there. And when it looks like nothing's going on there, that actually means it's continuous at negative 1. But anyways, let's maybe see 1 or 2 more of these. And while my page is loading, again, I'll just give you quick summary pictures here. So what does a jump discontinuity look like? Essentially it looks like this. Doesn't matter where the closed and open circles are, it just matters that for some reason your graph is suddenly cut into like 2 extreme pieces. What does a removable discontinuity look like? This, and you could have a filled in circle somewhere else on that vertical line where the open circle is. That's totally okay, but the idea is that it's connected, but it's not filled. That's what we call a removable discontinuity. And again, infinite discontinuity would be when you have something like this, or when they're going like different directions. That's going to be infinite. Again, I'll just go through this quickly now, see one more example, or one more set of examples. Hopefully my computer loads. Okay, select all the infinite discontinuities. Again, infinite discontinuities look like this somehow with a vertical asymptote. There are no vertical asymptotes this time, so the answer is none of the above. I wish I knew why it was going so slow. Maybe we'll just see 1 or 2 more of these and call it a video. Or at least call it done for this part of the assignment. Okay, all the removable discontinuities. So this time there are 2 of them. Again, that's when you have connection, but the circle is left unfilled. So that's happening at negative 3. Your side limits exist, your general limit exists, but your function's not defined at the same place. And it also happens here because, again, your side limits exist, your general limit exists, but the function value is not the same as what the limit's going towards. Or in other words, the hole is left unfilled and it's just been placed somewhere else. So those are your removable discontinuities. All right, and again, for the sake of the loading time of Khan Academy today, I'm going to call that the end of this part, and we'll do our third Khan Academy assignment. All right, so in our last Khan Academy assignment here is continuity over an interval. and this one is definitely special. All right, just making sure I was recording. So continuity over an interval, you have to think about the domain and range of a function. Now hopefully you've kind of been thinking about that because again, throughout this whole process of limits, you've been reading left to right and then telling what things have been doing vertically. What that means is you're considering the domain of the function first by moving left to right. You're considering the x values and then determining the y values, the range. Okay. Now that being said, when we're looking at on what intervals this graph is continuous, these are x values. And remember, this is interval notation. So what this means is from and including -3, so imagine a circle here, all the way up until, so follow the graph up until the x value +3, there we are, was my function continuous from -3 to +3? And the answer is no. And it's only not continuous for one particular place, 2. So there's a discontinuity going on at 2. This is again called a removable discontinuity. There's a hole, your side limits exist, your function limit or your general limit exists, but your function value doesn't agree with what the general limit is. That's a removable discontinuity. Again, it's like they've taken this point and removed it, and maybe they place it elsewhere, and maybe they don't. But the point is, there's one open circle removed from the rest of the connected graph. So not continuous there. What about from 3 to 5? 3 to 5, well, from here to here, yeah, no circle, no open circles, no infinite discontinuity, no jump, so it is continuous on 3 to 5. Again, I apologize for the slow loading times. I assure you it's not my internet. Or you know what, maybe it is my internet. Okay. Let me restart my Wi-Fi. Okay. So which functions are continuous over the interval -4 to 0? So again, we need to look at from x values -4 to 0, so -4 to 0. Did I see any crazy open circles or disconnections? No, I did not. So this one's continuous. Okay, and this is where things get really tricky. What about -4 to 0 here? From -4 to 0, that open circle means it is continuous from -4 to 0. Now, just to spoil it, we'll probably see it later, but I just need to say it now. What if for this blue graph, this orange graph, it said, is it continuous from closed bracket 0 to 2? That would be no, because the closed bracket 0 to 2, in other words, you're focusing on the right side, there's an open circle, so not continuous. So it does matter, your interval of continuity with this bracket, it means is 0 included? And if we're analyzing from the left-hand side of 0 and then including it, yes, that is true. Darn, restarting the Wi-Fi did not work, so something's up with Khan Academy this morning. But we're doing good. Okay, up next, on which interval is G continuous? So from -6 to -1. Again, that closed circle on -1 means we're good to go. Up next, from -1 to 1 with brackets means is this segment from -1 x value to 1 x value. And the endpoints, are they closed and filled? No, so do not check this one off. Again, the open circles means technically this is not true. All right, now if it was written in parentheses, because remember parentheses means not including for B, that would actually be true. So that's the difference between parentheses and brackets. And one more question. All right, so which ones are continuous from -3 to 1? Again, from -3 to 1. This one is because the closed circle's on the endpoint that I care about. From -3 to 1, this time I encounter a big infinite discontinuity. So definitely not. All right, now last thing while this loads and just confirms that I'm right. Again, it was -3 to 1. Really, discontinuity, think about the word continuous. From -3 to 1, we completely break the graph into 2 pieces. All right, so if you're breaking something, it's not continuous.